Synchronous Optical Networking and Synchronous Digital Hierarchy are standardized protocols that transfer multiple digital bit streams synchronously over optical fiber using lasers or highly coherent light from light-emitting diodes. At low transmission rates, data can also be transferred via an electrical interface. The method was developed to replace the Plesiochronous Digital Hierarchy system for transporting large amounts of telephone calls and data traffic over the same fiber without synchronization problems. SONET generic criteria are detailed in Telcordia Technologies Generic Requirements Document GR-499-CORE. Generic criteria applicable to SONET and other transmission systems are found in Telcordia GR-499-CORE. SONET and SDH, which are essentially the same, were originally designed to transport circuit mode communications from a variety of different sources, but they were primarily designed to support real-time, uncompressed, circuit-switched voice encoded in PCM format. The primary difficulty in doing this prior to SONET SDH was that the synchronization sources of these various circuits were different. This meant that each circuit was actually operating at a slightly different rate and with different phase. SONET SDH allowed for the simultaneous transport of many different circuits of differing origin within a single framing protocol. SONET SDH is not itself a communications protocol per se, but a transport protocol. Due to SONET SDH's essential protocol neutrality and transport-oriented features, SONET SDH was the obvious choice for transporting the fixed-length asynchronous transfer mode frames, also known as cells. It quickly evolved mapping structures and concatenated payload containers to transport ATM connections. In other words, for ATM, the internal complex structure previously used to transport circuit-oriented connections was removed and replaced with a large and concatenated frame into which ATM cells, IP packets, or Ethernet frames are placed. Both SDH and SONET are widely used today, SONET in the United States and Canada, and SDH in the rest of the world. Although the SONET standards were developed before SDH, it is considered a variation of SDH because of SDH's greater worldwide market penetration. The SDH standard was originally defined by the European Telecommunications Standards Institute, and is formalized as International Telecommunication Union Standards G707, G783, G784, and G803. The SONET standard was defined by Telcordia and American National Standards Institute Standard T1.105. Difference from PDH. SDH differs from Plesiochronous Digital Hierarchy in that the exact rates that are used to transport the data on SONET SDH are tightly synchronized across the entire network, using atomic clocks. This synchronization system allows entire inter-country networks to operate synchronously, greatly reducing the amount of buffering required between elements in the network. Both SONET and SDH can be used to encapsulate earlier digital transmission standards, such as the PDH standard, or they can be used to directly support either asynchronous transfer mode or so-called packet over SONET SDH networking. Therefore, it is inaccurate to think of SDH or SONET as communications protocols in and of themselves. They are generic, all-purpose transport containers for moving both voice and data. The basic format of a SONET SDH signal allows it to carry many different services in its virtual container, because it is bandwidth flexible. Protocol overview. SONET and SDH often use different terms to describe identical features or functions. This can cause confusion and exaggerate their differences. With a few exceptions, SDH can be thought of as a superset of SONET. SONET is a set of transport containers that allow for delivery of a variety of protocols, including traditional telephony, ATM, Ethernet, and TCP/IP traffic. SONET therefore is not in itself a native communications protocol per se and should not be confused as being necessarily connection-oriented in the way that term is usually used. The protocol is a heavily multiplex structure, with the header interleaved between the data in a complex way. This permits the encapsulated data to have its own frame rate and be able to float around relative to the SDH-SONET frame structure and rate. This interleaving permits a very low latency for the encapsulated data. Data passing through equipment can be delayed by at most 32 microseconds, a microsecond, compared to a frame rate of 125 a microsecond. Many competing protocols buffer the data during such transits for at least one frame or packet before sending it on. Extra padding is allowed for the multiplex data to move within the overall framing, as the data is clocked at a different rate than the frame rate. The protocol is made more complex by the decision to permit this padding at most levels of the multiplexing structure, but it improves all-around performance. The basic unit of transmission. The basic unit of framing in SDH is Stm-1, which operates at 155.520 megabits per second. SONET refers to this basic unit as an STS-3C. When the STS-3C is carried over OC3, it is often colloquially referred to as OC3C, but this is not an official designation within the SONET standard as there is no physical layer difference between an STS-3C and three STS-1s carried within an OC3. SONET offers an additional basic unit of transmission, the STS-1 or OC1, operating at 51.84 bits are exactly one-third of an Stm-1 OC3C carrier. This speed is dictated by the bandwidth requirements for PCM-encoded telephonic voice signals. At this rate, an STS-1/OC1 circuit can carry the bandwidth equivalent of a standard DS3 channel, which can carry 672/64 kbits voice channels. In SONET, the STS-3C signal is composed of three multiplexed STS-1 signals. The STS-3C may be carried on an OC3 signal. Some manufacturers also support the SDH equivalent of the STS-1/OC1, known as STMO. Framing. In packet-oriented data transmission, such as Ethernet, a packet frame usually consists of a header and a payload. The header is transmitted first, followed by the payload. In synchronous optical networking, this is modified slightly. The header is termed the overhead, and instead of being transmitted before the payload, is interleaved with it during transmission. Part of the overhead is transmitted, then part of the payload, then the next part of the overhead, then the next part of the payload, until the entire frame has been transmitted. In the case of an STS-1, the frame is 810 octets in size, while the Stm-1/STS-3C frame is 2430 octets in size. For Streets 1, the frame is transmitted as 3 octets of overhead, followed by 87 octets of payload. This is repeated 9 times, until 810 octets have been transmitted, taking 125 a microsecond. In the case of an STS-3C Stm-1, which operates 3 times faster than an STS-1, 9 octets of overhead are transmitted, followed by 261 octets of payload. This is also repeated 9 times until 2430 octets have been transmitted, also taking 125 a microsecond. For both SONET and SDH, this is often represented by displaying the frame graphically, as a block of 90 columns and 9 rows for STS-1, and 270 columns and 9 rows for Stm-1/STS-3C. This representation aligns all the overhead columns, so the overhead appears as a contiguous block, as does the payload. The internal structure of the overhead and payload within the frame differs slightly between SONET and SDH, and different terms are used in the standards to describe these structures. Their standards are extremely similar in implementation, making it easy to interoperate between SDH and SONET at any given bandwidth. In practice, the terms STS-1 and OC1 are sometimes used interchangeably, though the OC designation refers to the signal in its optical form. It is therefore incorrect to say that an OC3 contains 3 OC1s, an OC3 can be said to contain 3 STS-1s. SDH frame. The Stm-1 frame is the basic transmission format for SDH, the first level of the synchronous digital hierarchy. The Stm-1 frame is transmitted in exactly 125 AA microsecond, therefore, there are 8,000 frames per second on a 155.52 Mbit SoC3 fiber optic circuit. The Stm-1 frame consists of overhead and pointers plus information payload. The first 9 columns of each frame make up the section overhead and administrative unit pointers, and the last 261 columns make up the information payload. The pointers identify administrative units within the information payload. Thus, an OC3 circuit can carry 150.336 Mbit of payload, after accounting for the overhead. Carried within the information payload, which has its own frame structure of 9 rows and 261 columns, are administrative units identified by pointers. Also within the administrative unit are one or more virtual containers. VCs contain path overhead and VC payload. The first column is for path overhead. It is followed by the payload container, which can itself carry other containers. Administrative units can have any phase alignment within the STM frame, and this alignment is indicated by the pointer in row 4. The section overhead of a STM1 signal is divided into 2 parts, the regenerator section overhead and the multiplex section overhead. The overheads contain information from the transmission system itself, which is used for a wide range of management functions, such as monitoring transmission quality, detecting failures, managing alarms, data communication channels, service channels, etc. The STM frame is continuous and is transmitted in a serial fashion, byte by byte, row by row. Transport overhead. The transport overhead is used for signaling and measuring transmission error rates, and is composed as follows: section overhead, called a SOH in SDH terminology, 27 octets containing information about the frame structure required by the terminal equipment. Line overhead, called MSOH in SDH, 45 octets containing information about error correction and automatic protection switching messages as may be required within the network. AU pointer, points to the location of the J1 byte in the payload. Path virtual envelope, data transmitted from end to end is referred to as path data. It is composed of 2 components, payload overhead, 9 octets used for end-to-end signaling and error measurement. Payload, user data, for streets 1, the payload is referred to as the synchronous payload envelope, which in turn has 18 stuffing bytes, leading to the STS1 payload capacity of 756 bytes. The streets 1 payload is designed to carry a full PDH-DS3 frame. When the DS3 enters the SONET network, path overhead is added, and that SONET network element is said to be a path generator and terminator. The SONET-NE is line terminating if it processes the line overhead. Note that wherever the line or path is terminated, the section is terminated also. SONET regenerators terminate the section, but not the paths or line. And streets 1 payload can also be subdivided into 7 virtual tributary groups. Each VTG can then be subdivided into 4 VT 1.5 signals, each of which can carry a PDH-DS1 signal. A VTG may instead be subdivided into 3 VT2 signals, each of which can carry a PDH-E1 signal. The SDH equivalent of a VTG is a TUG2. VT 1.5 is equivalent to VC11, and VT2 is equivalent to VC12. 3 streets 1 signals may be multiplexed by time division multiplexing to form the next level of the SONET hierarchy, the OC3, running at 155.52 Mbit/s. The signal is multiplexed by interleaving the bytes of the 3 STS1 frames to form the STS3 frame, containing 2,430 bytes and transmitted in 125 AA microsecond. Higher speed circuits are formed by successively aggregating multiples of slower circuits, their speed always being immediately apparent from their designation. For example, 4 STS3 or AU4 signals can be aggregated to form a 622.08 Mbit/s signal designated OC12 or STM4. The highest rate commonly deployed is the OC768 or STM256 circuit, which operates at rate of just under 38.5 bits. Where fiber exhaustion is a concern, multiple SONET signals can be transported over multiple wavelengths on a single fiber pair by means of wavelength division multiplexing, including dense wavelength division multiplexing and coarse wavelength division multiplexing. DWDM circuits are the basis for all modern submarine communications cable systems and other long-haul circuits. SONET SDH and relationship to 10 gigabit Ethernet. Another type of high-speed data networking circuit is 10 gigabit Ethernet. The Gigabit Ethernet Alliance created two 10 gigabit Ethernet variants, a local area variant with a line rate of 10.3125 Gbps, and a wide area variant with the same line rate as OC192/STM64. The 1PHY variant encapsulates Ethernet data using a lightweight SDH SONET frame, so as to be compatible at a low level with equipment designed to carry SDH SONET signals, whereas the LANPHY variant encapsulates Ethernet data using 64B/66B line coding. However, 10 gigabit Ethernet does not explicitly provide any interoperability at the bitstream level with other SDH SONET systems. This differs from WDM system transponders, including both coarse and dense wavelength division multiplexing systems that currently support OC192 SONET signals, which can normally support thin SONET Euroframe 10 gigabit Ethernet. SONET SDH data rates. User throughput must not deduct path overhead from the payload bandwidth, but path overhead bandwidth is variable based on the types of cross-connects built across the optical system. Note that the data rate progression starts at 155 Mbps and increases by multiples of 4. The only exception is OC24, which is standardized in ANSIT 1.105, but not a SDH standard rate in ITU-TG 707. Other rates, such as OC9, OC18, OC36, OC96, and OC1536, are defined but not commonly deployed. Most are considered orphaned rates. Physical layer. The physical layer refers to the first layer in the OSI networking model. The ATM and SDH layers are the regenerator section level, digital line level, transmission path level, virtual path level, and virtual channel level. The physical layer is modeled on three major entities: transmission path, digital line and the regenerator section. The regenerator section refers to the section and photonic layers. The photonic layer is the lowest SONET layer and it is responsible for transmitting the bits to the physical medium. The section layer is responsible for generating the proper STSN frames which are to be transmitted across the physical medium. It deals with issues such as proper framing, error monitoring, section maintenance, and order wire. The line layer ensures reliable transport of the payload and overhead generated by the path layer. It provides synchronization and multiplexing for multiple paths. It modifies overhead bits relating to quality control. The path layer is SONET's highest level layer. It takes data to be transmitted and transforms them into signals required by the line layer, and adds or modifies the path overhead bits for performance monitoring and protection switching. SONET SDH network management protocols. Overall functionality. Network management systems are used to configure and monitor SDH and SONET equipment either locally or remotely. The systems consist of three essential parts, covered later in more detail: software running on a network management system terminal, for example workstation, dumb terminal or laptop housed in an exchange/central office. Transport of network management data between the network management system terminal and the SONET/SDH equipment, for example using Tl1/Q3 protocols. Transport of network management data between SDH/SONET equipment using dedicated embedded data communication channels within the section and line overhead. The main functions of network management thereby include network and network element provisioning. In order to allocate bandwidth throughout a network, each network element must be configured. Although this can be done locally, through a craft interface, It is normally done through a network management system that in turn operates through the SONET SDH network management network. Software upgrade. Network element software upgrades are done mostly through the SONET SDH management network in modern equipment. Performance management. Network elements have a very large set of standards for performance management. The performance management criteria allow not only monitoring the health of individual network elements, but isolating and identifying most network defects or outages. Higher-layer network monitoring and management software allows the proper filtering and troubleshooting of network-wide performance management, so that defects and outages can be quickly identified and resolved. Consider the three parts defined above: network management system terminal, local craft interface. Local craftspersons can access a SDH/SONET network element on a craft port, and issue commands through a dumb terminal or terminal emulation program running on a laptop. This interface can also be attached to a console server, allowing for remote out-of-band management and logging. Network management system. This will often consist of software running on a workstation covering a number of SDH/SONET network elements, Tl1/Q3 protocols. Tl1, SONET equipment is often managed with the Tl1 protocol. Tl1 is a telecom language for managing and reconfiguring SONET network elements. The command language used by a SONET network element, such as Tl1, must be carried by other management protocols, such as SNMP, CORBA, or XML. Q3, SDH has been mainly managed using the Q3 interface protocol suite defined in ITU recommendations Q811 and Q812. With the convergence of SONET and SDH on switching matrix and network elements architecture, newer implementations have also offered Tl1. Most SONETNEs have a limited number of management interfaces defined: Tl1 Electrical Interface. The electrical interface, often a 50-ohm coaxial cable, sends SONET Tl1 commands from a local management network physically housed in the central office where the SONET network element is located. This is for local management of that network element and, possibly, remote management of other SONET network elements. Dedicated embedded data communication channels. SONET and SDH have dedicated data communication channels within the section and line overhead for management traffic. Generally, section overhead is used. According to ITU TG 7712, there are three modes used for management: IP-only stack, using PPP as data link; OSI-only stack, using LAPD as data link; dual stack using PPP or LAPD with tunneling functions to communicate between stacks. To handle all of the possible management channels and signals, most modern network elements contain a router for the network commands and underlying protocols. Equipment. With advances in SONET and SDH chipsets, the traditional categories of network elements are no longer distinct. Nevertheless, as network architectures have remained relatively constant, even newer equipment can be examined in light of the architectures they will support. Thus, there is value in viewing new, as well as traditional, equipment in terms of the older categories. Regenerator. Traditional regenerators terminate the section overhead, but not the line or path. Regenerators extend long-haul routes in a way similar to most regenerators, by converting an optical signal that has already traveled a long distance into electrical format and then retransmitting a regenerated high-power signal. Since the late 1990s, regenerators have been largely replaced by optical amplifiers. Also, some of the functionality of regenerators has been absorbed by the transponders of wavelength division multiplexing systems. Add-drop multiplexer. Add-drop multiplexers are the most common type of network elements. Traditional ADMs were designed to support one of the network architectures, though new generation systems can often support several architectures, sometimes simultaneously. ADMs traditionally have a high-speed side, and a low-speed side, which can consist of electrical as well as optical interfaces. The low-speed side takes in low-speed signals, which are multiplexed by the network element and sent out from the high-speed side, or vice versa. Digital cross-connect system. Recent digital cross-connect systems support numerous high-speed signals, and allow for cross-connection of DS1S, DS3S and even STS3/12C and so on, from any input to any output. Advanced DCSs can support numerous subtending rings simultaneously. Network architectures, SONET and SDH have a limited number of architectures defined. These architectures allow for efficient bandwidth usage as well as protection, and are fundamental to the worldwide deployment of SONET and SDH for moving digital traffic. Every SDH-SONET connection on the optical physical layer uses two optical fibers, regardless of the transmission speed. Linear automatic protection switching. Linear automatic protection switching, also known as 1+1, involves 4 fibers, 2 working fibers, and 2 protection fibers. Switching is based on the line state, and may be unidirectional, or bidirectional. Unidirectional path-switched ring. In unidirectional path-switched rings, 2 redundant copies of protected traffic are sent in either direction around a ring. A selector at the egress node determines which copy has the highest quality, and uses that copy, thus coping if one copy deteriorates due to a broken fiber or other failure. UPSRs tend to sit nearer to the edge of a network, and as such are sometimes called collector rings. Because the same data is sent around the ring in both directions, the total capacity of a UPSR is equal to the line rate N of the OCN ring. For example, in an OC3 ring with 3 STS1s used to transport 3 DS3s from ingress node A to the egress node D, 100% of the ring bandwidth would be consumed by nodes A and E. Any other nodes on the ring could only act as pass-through nodes. The SDH equivalent of UPSR is subnetwork connection protection. SNCP does not impose a ring topology, but may also be used in mesh topologies. Bidirectional line-switched ring. Bidirectional line-switched ring comes in 2 varieties, 2-fiber BLSR and 4-fiber BLSR. BLSRs switch at the line layer. Unlike UPSR, BLSR does not send redundant copies from ingress to egress. Rather, the ring nodes adjacent to the failure reroute the traffic the long way around the ring on the protection fibers. BLSRs trade cost and complexity for bandwidth efficiency, as well as the ability to support extra traffic that can be preempted when a protection switching event occurs. In 4-fiber ring, either single node failures, or multiple line failures can be supported, since a failure or maintenance action on one line causes the protection fiber connecting 2 nodes to be used rather than looping it around the ring. BLSRs can operate within a metropolitan region or, often, will move traffic between municipalities. Because a BLSR does not send redundant copies from ingress to egress, the total bandwidth that a BLSR can support is not limited to the line rate N of the OCN ring, and can actually be larger than N depending upon the traffic pattern on the ring. In the best case, all traffic is between adjacent nodes. The worst case is when all traffic on the ring egresses from a single node, that is, the BLSR is serving as a collector ring. In this case, the bandwidth that the ring can support is equal to the line rate N of the OCN ring. This is why BLSRs are seldom, if ever, deployed in collector rings, but often deployed in inter-office rings. The SDH equivalent of BLSR is called multiplex section shared protection ring. Synchronization. Clock sources used for synchronization in telecommunications networks are rated by quality, commonly called a stratum. Typically, a network element uses the highest quality stratum available to it, which can be determined by monitoring the synchronization status messages of selected clock sources. Synchronization sources available to a network element are local external timing. This is generated by an atomic cesium clock or a satellite-derived clock by a device in the same central office as the network element. The interface is often a DS1, with sync status messages supplied by the clock and placed into the DS1 overhead. Line-derived timing. A network element can choose to derive its timing from the line level, by monitoring the S1 sync status bytes to ensure quality. Holdover. As a last resort, in the absence of higher quality timing, a network element can go into a holdover mode until higher quality external timing becomes available again. In this mode, the network element uses its own timing circuits as a reference. Timing loops. A timing loop occurs when network elements in a network are each deriving their timing from other network elements, without any of them being a master timing source. This network loop will eventually see its own timing float away from any external networks, causing mysterious bit error, and ultimately, in the worst cases, massive loss of traffic. The source of these kinds of errors can be hard to diagnose. In general, a network that has been properly configured should never find itself in a timing loop, but some classes of silent failures could nevertheless cause this issue. Next generation SONET/SDH. SONET/SDH development was originally driven by the need to transport multiple PDH synchronously like DS1, E1, DS3, and E3 along with other groups of multiplexed 64 kbits pulse code modulated voice traffic. The ability to transport ATM traffic was another early application. In order to support large ATM bandwidths, concatenation was developed, whereby smaller multiplexing containers are inversely multiplexed to build up a larger container to support large data-oriented pipes. One problem with traditional concatenation, however, is inflexibility. Depending on the data and voice traffic mix that must be carried, there can be a large amount of unused bandwidth left over, due to the fixed sizes of concatenated containers. For example, fitting a 100 Mbps fast Ethernet connection inside a 155 Mbps STS3C container leads to considerable waste. More important is the need for all intermediate network elements to support newly introduced concatenation sizes. This problem was overcome with the introduction of virtual concatenation. Virtual concatenation allows for a more arbitrary assembly of lower-order multiplexing containers, building larger containers of fairly arbitrary size without the need for intermediate network elements to support this particular form of concatenation. Virtual concatenation leverages the x86 or generic framing procedure protocols in order to map payloads of arbitrary bandwidth into the virtually concatenated container. The link capacity adjustment scheme allows for dynamically changing the bandwidth via dynamic virtual concatenation, multiplexing containers based on the short-term bandwidth needs in the network. The set of next-generation SONET/SDH protocols that enable Ethernet transport is referred to as Ethernet over SONET/SDH. See also, List of device bandwidths, routing and wavelength assignment, multi-wavelength optical networking, optical mesh network, optical transport network, G709, notes. References. External links, Understanding SONET/SDH. The Queen's University of Belfast SDH SONET Primer, SDH Pocket Handbook from Actina JDSU, SONET Pocket Handbook from Actina JDSU, the SONET homepage, SONET Interoperability Form, Network Connection Speeds Reference, Next Generation SDH, The Future Looks Bright, The Future of SONET/SDH, Standards, Telcordia GR-499-CORE, SONET Transport Systems, Common Generic Criteria, Telcordia GR-499-CORE, Transport Systems Generic Requirements, Common Requirements, ANSI T1.105 SONET, Basic Description including multiplex structure, rates and formats, ANSI T1.119/ATISPP. 09001119.01.2006, SONET, Operations, Administration, Maintenance, and Provisioning, Communications, ITUT Recommendation G707, Network Node Interface for the Synchronous Digital Hierarchy, ITUT Recommendation G783, Characteristics of Synchronous Digital Hierarchy Equipment Functional Blocks, ITUT Recommendation G803, Architecture of Transport Networks based on the Synchronous Digital Hierarchy.